Todd, what's with all this stuff?
Well, B, you can use this equipment to measure the melting point of a solid compound. That's the temperature at which sufficient energy is available to break apart the crystal lattice structure and the solid changes to a liquid. This physical property of the solid will help assess its purity and also its identity.
Okay, so how does a melting point tell us about purity?
That's a good point, Earl. If you think about it, in a pure sample, all the components are the same and they would therefore behave the same, and the observed melting point will be a very sharp, narrow range. An impure sample will have different components, and the result will be an observed melting point that is lower than it is expected to be, and it also occurs over a wider range. Okay, so how about you guys doing some melting points now?
What are we supposed to do with these tube thingies?
You mean the melting point tubes? What do you think they're used for?
To put the sample in?
Very good, Phil. Now, packing the sample in the melting point tube is important. The sample should be well crushed and dry, and only about a 2 millimeter height of sample is required. An improperly packed melting point sample could lead to difficulties in identifying the point when melting begins, and may also result in a larger observed melting point range.
You know, when we measure the melting point, we just stick the sample in here and watch it?
What's that instrument called again?
The Gala lamp or something?
Okay, close. The gallon camp has one larger hole for your thermometer and 3 smaller holes for sample tubes.
Does this knob set the temperature or something?
Not exactly. The rheostat controls the rate of heating. The higher the setting, the faster the temperature will rise. In practice, though, each gallon camp is a little different, so you should try and get a feel for how yours works and the temperature changes that are occurring at the different setting.
Well, that's easy. If I just set it at the maximum value, then I'll be done in no time.
Sure, you may choose to do that if you want to get an unreliable value, but it makes more sense to do it correctly, right? What can be done is to heat the sample up rapidly until about 15 degrees below the expected melting point, then turn the rheostat setting down so that over the final 10 degrees, the temperature is changing only about 1 degree or so per minute.
And this boost switch is for?
It's used for compounds with melting points greater than 230 degrees. We usually don't use it though.
Do we have to wait until it cools all over again to put the next sample in?
Yeah, do we have to put it back to 0?
Now let's think about that, Phil. If you're going to measure a higher melting point sample, then you can just keep on going. But if the next sample has a lower melting point, then it has to cool to about 15 degrees below that value before you can resume heating.
So when you're observing it actually decompose to a liquid, melt into a liquid, you take the temperature when you first see a drop, and again when it's a liquid?
Yeah, that sounds pretty good, Crystal. When you watch a sample melt, you may first see it start to shrink, and maybe you'll see some bubbles, like perspiration, above the sample. But you want to record the starting temperature when you see a drop of liquid in the bulk of the sample, and then record the final temperature when the last bit of the bulk of the sample turns into a liquid. This is the melting point range.
So that's all there is to it?
No. I wouldn't make it that easy on you now, would I? What makes you think that the temperatures you read off the thermometer are accurate?
What? You mean these things aren't calibrated?
Well, many thermometers vary in accuracy over their entire temperature range. So, any ideas on how the calibration could be done?
Couldn't we measure the melting points of known compounds?
Good idea, Earl. By measuring the melting points of selected melting point standards, the temperature range of a thermometer can be calibrated. We can then draw a thermometer calibration graph, which plots the observed melting points versus the actual or literature melting points. The graph can then be used to calibrate all further readings done with that thermometer by interpolation to give the actual temperature that should be reported. In order to get the 0 point, ice water can be used.
So when we do the ice water one, do we use the same melting point tube?
Come on, ice water in a tube?
I think what B is so tactfully trying to get across to you, Phil, is that the 0 reading can simply be done by measuring the temperature of a beaker of ice water.
Like this compound, the range it had on the bottle was 113 to 115, and the range I saw was 107 to 109. So I just graph 114 and 108, or something like that?
Sure, Crystal. To be consistent, it's a good idea to plot the midpoint values of the observed and actual melting point ranges.
So, once we have calibrated our melting point, we can then finally identify what our solid unknown compound is, right?
Let me ask you this. What if there were 2 possible compounds with very similar melting points? What would you do then?
Uh-oh.
Well, try to see if you can follow what I'm getting at here. The technique of taking mixture melting points involves crushing together equal amounts of unknown sample with one of the possibilities, say compound A, for example, and then measuring its melting point. A second tube could be prepared the same way using the unknown and the other possibility, compound B, for example, and measuring its melting point. Now, try to remember back to when we talked about the melting points of pure and impure samples. Can you now predict what we might see at this stage? Anyone? Okay, let me rephrase that then. If one of the tubes has identical components in it and the other has 2 different components in it, what types of melting point ranges can be expected?
Don't pure samples give narrow melting ranges and impure samples give depressed, broad melting point ranges?
Yeah, so the mixture that gives the same melting point as the unknown must be made up of the same compound.
Hey, that gives us the identity of our unknown compound.
See, Todd? I told you I knew what I was doing in the lab.
Hey, you're right. You guys are off to a great start. I guess I'm going to have to expect better and better things from you from now on. Anyway, that's enough of that. Let's get back to work.